everybody. Thanks for coming to the talk. My name's Sourav Dey. I'm Managing Director at Manifold. Quick background on Manifold. Probably haven't heard of us. We're a relatively new engineering services firm with offices here in the Valley and also in Boston. My background, I'm a managing director there, leading the machine learning practice. I'm myself PhD in computer science from MIT, almost a decade of work as an algorithms engineer. Both making real-time algorithms running on an embedded target all the way to gigantic data sets at Google working in the cloud. The point of this talk is really synthesizing a lot of those learnings from the last decade and beyond, and from particularly our time at Manifold about the process of doing machine learning, of doing AI. And that's really what I wanted to communicate in this talk. We've come up with kind of some best practices, some mental models, so to speak, that I wanted to share with you guys. We put it on this umbrella of lean AI, because the point of this mental models is really to deliver business value as quickly as possible from AI. And I'll make it real using a couple of case studies from our work. So what is our framework? We call it lean AI. It has 6 steps. Understand, oh cool, look at that. Understand, engineer, modeling, user feedback, deploying, and validation. As a machine learning engineer, we often spend or think this is the most important thing. Modeling, put out the best generative adversarial network or the latest and greatest recurrent neural network. This is just one small piece of the puzzle. It's oftentimes these things that come before and these things come after that most of the risk in the project lies. And I want to focus on that more in this talk. I'm probably not going to get to talk about all of these things, but I'll try to cover a little bit of understanding, a little bit of modeling, a little bit of user feedback, and some more high-level things on the other 3. So let me jump in. Understand. What do I mean by understand? 2 things, understanding the data and understanding the business use case. And I capture it, PhD habits die hard. I have to have one slide with LaTeX on there. And so this is my one slide. What is it saying? The value that you get out of your AI is upper bounded by the business value of the problem you're trying to solve, the data quality that you have on hand to solve that problem, and then the last one is the predictive signal in that data. The last one is something you can't control, really. That's just kind of the physics. But what you can control up front is where you point doing the machine learning problem that you want to solve and assessing the data quality. And the kind of depressive thing is if any of these things go to 0, the value of the AI goes to 0. It's multiplicative. So how do you combat that? I don't want to, and I've been in companies and situations before where there'll be months, years-long projects that ultimately get very little value. People lose their kind of faith in machine learning to drive value for their business. I truly believe that machine learning can drive value for all businesses if done appropriately. And so a lot of our work as Manifold is about this up front, assessing those things so that we make sure that we're delivering value for our clients, the business is getting value out of the machine learning. How do we do that? We make something we call just an AI spec. And so this is none of this is magic. This is all just good engineering practices codified. What am I trying to get into that spec? Part of it is really understanding the business. What is the ROI if I solve this problem? What are the pressing needs for the business? If I could solve this, who would use it? Who would get value out of it? How much recurring revenue could you get if you solve this problem? So we usually get all the stakeholders in the room and have half-day, full-day workshop to really surface all of the problems in the business and understand them and put the lens of machine learning on them. So that's understanding the wants. On the other side is we're sitting down with the technical stakeholders and really understanding the data that is available today, that could be available in the future. And we do a very, very detailed data audit. And like a lot of the questions that we're trying to answer is, you heard in the previous talk, is like, where are your data sources? How much data is there? Where are they coming from? Is it all laid down in a warehouse already? Is part of it laid down in a warehouse? Is part of it not laid down in a warehouse? Kind of looking at some of the business needs, how rare are the events? Are things labeled well? Are things joinable? Entity resolution is a problem that we often face of multiple data sets are not joinable. So looking at things from both angles, we want to find things where there's overlap, and that's what we're looking for. And we really deliver that literally as a spec, and I'll show you an example of that. So one example that I'll be talking about throughout this talk is one of our biggest clients was the leading baby registry in the United States. And their CEO and CTO hired our firm because they wanted to be more customer-centric. They know from doing some data analytics that 20% of my customers are driving 80% of my revenue. How do I get more customers like them? How do I give these customers more value so that they're having a better customer experience and I ultimately have a higher revenue? For their problem, what we ended up doing is we sat for a whole day with their business team and really understood their business at a really, really deep level about how they're marketing, who's a visitor, who signs up, how signups become adopters, how adopters activate, and all of these have very, very specific business metrics and actions associated with this. For example, there's visitors to their website, they sign up, they make an account. Adopters, they add a single item to the registry. Activate means that something was purchased off of that registry, and ultimately, a very, very, very small percentage of the people that they marketed to are high LTV users that they're buying $500+ $1,000+ worth of items from the baby registry. Their biggest problem turns out, we started very unstructured, like you saw the aspiration that the CEO had, but it turned out their most pressing problem was decision velocity. They couldn't make decisions quickly because after somebody signed up, they didn't know if they were a high LTV customer until 9 months later, baby registry, that's where it comes from. So their problem was like, look, I want to A/B test marketing campaigns. I want to A/B test different product changes, but I can't make decisions because I have to wait 9 months to see if anything happened materially to my bottom line because of these changes. Can you help us make decisions more quickly? What we ended up looking at their data as well. Again, they had many different sorts of data. They had the heap analytics data. They had mixed panel data from their mobile app. They had data, of course, in their transactional database of people adding things to the registry and things like that. We ended up settling on, we're going to create a model to predict if the customer is going to adopt, activate, and even predict their LTV after 9 months every day of the customer journey. So the person signs up. After 1 day, after 2 days, after 7 days, after 30 days, I'm going to make a prediction of how much LTV there's going to be, whether they're going to activate, whether they're going to adopt. And that prediction for every single one of their customers will help them make decisions more quickly because they can look at that prediction 7 days in and make a decision on whether these 2 marketing campaigns were effective or which one was more effective, whether these product changes. So, like Google, for example, in the pay-per-click world, you can A/B test with ground truth. They're going to A/B test with predicted customer lifetime value. That's what we were driving toward. And we agreed on it, and this is what we wanted to build toward. And I'll talk more about how we got there quickly in a second. Another big customer that we had was a leading oil field services company. So this is a company out of Oklahoma. And they have thousands of gas compressors out at well sites that are internet connected, that are sending up very, very fine tick sensor data back up to their data lake. Their problem was we get paid for uptime. That's the business model. They don't sell the unit, they lease the unit, pay me for uptime. So somewhat like the GE model for airplane engines. So if things go down, they're losing money. In addition, maintenance is a part of their service contract, so they have to roll a truck. That's their largest cost center. So their goal was, can we be more efficient about maintenance and increase uptime so that we're just making more money and we're delivering more value to our customers? How do we do that? This one was a much gnarlier problem because they had many, many different sources of data. They had the sensor data streams coming off of the machines. They had an entire workflow software for their maintenance techs where they, almost 5 years of history where the maintenance techs had gone in and they're logging what they're doing, what kind of work they're doing on the machines, why they're rolling the truck, things like that. When push came to shove, we found a lot of things. The biggest problem was that they had a dream of, hey, we want to find this failure, we want to find this failure, we want to find this failure. Turns out, in their historical, about 5 years of data, they didn't have accurate labeling on their data. This was not labeled well enough because what would happen is the maintenance techs are just replacing parts, so we know what parts they're replacing, but oftentimes those replacement of parts is a triage process in and of itself. So you don't know what the root cause of what caused the failure was not marked for large parts of the history. So turns out that building the models that they wish they had was not possible using the data they had. So one thing we did do is we pointed them, hey, we should make some new fields in this workflow software so that going forward, we have better data labeled in the future. But we didn't want to just throw away the 5 years of history. What we ended up doing is we decided on a spec where we're going to predict if major faults are going to happen. So this is what happened essentially is that we only trusted the machine-generated data because that was, I know the machine went down. That is accurately represented in the sensor data streams. So what we were trying to predict is that if the machine was down for greater than 2 hours, and there was actually many, many times the machine would go down for less than 2 hours, where like a simple hardware reset or software reset would just bring the machine back up. It's kind of very typical in many of these oil field operations that it's kind of like kicking the side of the TV and it works again. There's something temporary that happened. But things that were more than 2 hours are considered major faults because typically if this happened, you're almost always rolling a truck or there's a customer call. So this is the thing we're trying to predict. We're trying to predict whether that's going to happen 1 day, 2 day, 5 days ahead was really like the sweet spot because then they could do turn unplanned maintenance into planned maintenance. We only decided to look at the machine-generated data because the human-generated data just had so many data quality issues. So this is, again, the spec that we settled on by understanding their business problem, understanding their data, merging the two to really come up with that spec. And so this was important to communicate that up front to the stakeholders so that they know that in the end, this is just engineering. It's not fairy dust that you're sprinkling and it's AI is going to solve your problem. It is really about the data and about whether you can do anything with that data. So that highlights some of the things that we do in understanding. I'm going to skip over engineering in a second. I'll cover it a little bit in modeling, but I wanted to cover some of the mental models that we use in the modeling phase of Lean AI. One thing, very important thing I'll mention is modeling is just the tip of the pyramid. This is a diagram that one of our friends of the firm, Monica Ragati, she was one of the first data scientists at LinkedIn. She made this diagram. I think it's fantastic. It's kind of like Maslow's hierarchy of needs. This is the data science hierarchy of needs. Modeling is up at the top. It's built on a foundation of very, very, very solid data engineering. And so this is, I didn't cover it, but data engineering is a huge part of the work that we do. In fact, half of our practice is focused on a lot of data engineering type of things, using open source tools, using vendors to do that. But we want to do modeling. This is another thing that I've seen managing data science teams and machine learning engineers. People want to make the fanciest thing. You know, they're like, I read about this thing that came out in CVPR 2 weeks ago, and we should do this 3D convolutional network. And I'm always like, we should do division. Like, that should be the first thing we try. Because you need a baseline. And that's really what this slide is trying to communicate. A baseline model is the simplest model that you can put into production that has some value, and then we will iteratively improve on that. And I actually have some very specific opinions to that end that I'm trying to like canonize in Lean AI, but even if your problem is a regression problem, I prefer to cast it as a classification problem as first, because class errors are much easier to debug and understand and learn from than regression errors. In addition, if it's a predictive analytics type of problem, I always prefer to start with a random forest first, then go to the more complicated gradient boosted trees, and then go to deep learning. If it's a computer vision or NLP type problem, yeah, I'll start with deep learning, but typically I'm just using a pre-trained neural network. Maybe then I'll fine-tune it in V2, and then maybe I'll train my own architecture from scratch in V3. In addition, if I'm doing feature engineering, which is almost always the case in predictive analytics type of problems, pick a very few features to start, layer in more as time goes on, because in the end, most of the time is spent doing feature engineering. So this just grows linearly with the number of features you want to make. So, oh yeah, before I get into the case studies, the key is you always have to evaluate how your model's doing, but you want to evaluate to learn. And so what does that mean? To me, it means two things. One, of course, look at aggregate metrics, right? Look at the ROC curve if you're making a classifier, cross-validated ROC, validation loss if you're doing deep learning. That's all great, but something that, that I haven't seen very much in practice when you, especially with junior engineers, look at the individual metrics. And we make it a point to look at that. We look at, hey, what is the model doing for particular examples? So this is a PDF of the prediction probability PDF. So the red are the ones that are actually true, and the blues are the ones that are actually false, so they're actually 0. And as you can see, there's some that I'm predicting well, but there's many actually true examples that I'm not predicting well in this particular, I don't know where I pulled this from for one of our models. So what is happening here? Who are these people where the ground truth was true, but the model's doing so poorly? Why is it doing so poorly? So really getting down to looking at the data and understanding what's happening leads to a lot of insight about what features I should generate, how I should change the architecture, how I should perhaps even change the modeling paradigm altogether. And so we can talk more about this later if you want, but I think this is really, really important. It's not, written about very much. So what does this mean in practice? So let's go back to our baby registry problem. We started with, so what I'm showing here is the 7-day model. So this is, can I predict if LTV is going to be 0 7 days after sign up? The first thing we did is we made 2 features. We made 2 features, which was what platform did the user use to sign up? So there's essentially, it was iOS, Android, and then we broke down the web into the different web browsers, Chrome, Safari, Internet Explorer. And then we looked at refer, which was where did they come from? Pinterest, directly from the web, Facebook, Instagram. We started with these 2 features because they were really, really easy to engineer. It was just like literally in the transactional database or inside Heap Analytics, throw it in the model, not doing great. AUC of 0.65, okay. But then, very quickly, within the first week, we added 9 more features. So some of them were features that were about early activation. How much money did they add in the first day, in the first few days? How many items did they add in the first few days? How long were their sessions? So added those simple features in, getting AUC of 0.9. And at that point, it doesn't make sense to go to deep learning or gradient boosting trees. This is like adding a lot of value right now. Let's deploy this into production. Let's move on to another problem. And so this is the importance of doing baseline models iteratively. you can do early stopping in your engineering work. By contrast, on our oil and gas problem, here we had to do a lot of engineering work up front to get the data in a format where we could even do machine learning. So that was, I'm omitting all of that, but we had a Spark pipeline, had a Dask pipeline, HDF5 files, and all this stuff. We wrote some features to make features such as frequencies and rolling averages, rolling standard deviations. Put that into a tree-based model, put a few features in there, really not great AUC, 0.65. Added more features, got a little bit better AUC, 0.78. Added more and more and more features, really this started to saturate. So, okay, not great. We tried deep learning after that. So we went to a convolutional neural network, a multi-scale convolutional neural network inspired by WaveNet. Tried to tune that for almost 2 weeks. Really did not get material improvement in the ROC. In fact, what happened, it took a lot of tuning to even match the hand feature engineered tree-based methods. And so at this point, we were decided that, like, look, I think we're seeing diminishing returns. There's something, where it's not doing well, there's really no way to discern. The data is not showing anything. Human experts, when we went to the maintenance techs, weren't able to see anything. And so there's something fundamentally unpredictable about what's happening. And there's various hypotheses we had. I think we wanted to incorporate a more detailed weather stream, perhaps. The data that was being sent up was instantaneously sampled once a minute, so we're losing all of the high frequency information that is finely sampled at megahertz on the device. So there is potentially just the data quality was not good enough to get any better than this. So we had these dreams of going to a mixed effects model. We're like, meh, it's really not worth doing this right now. We should continue moving around the circle of the 6 steps and come back to that if we have time to make continued investment in this. Which brings me to the last one I wanted to cover, user feedback. What do I mean by user feedback? What I mean by user feedback is most of the machine learning algorithms that we're making are in the end consumed by a human. So in both of these examples, the baby registry example, those predictions are consumed by the product team and by the marketing team. In the oil and gas example, those predictions are consumed by the engineering and the maintenance teams. So we wanted to get this in front of them as fast as possible to see how they're going to react to it and observe how it's going to change their workflow, how it could change their workflow, and see what they think of it. And so, again, none of this is magic. This is, if you think of human-centered design that IDEO made popular, this is very much in line with that. And we didn't make fancy web apps. Literally, we would have our machine learning service cut an Excel report. And then we would just deliver this Excel report once a day in an email and see what the maintenance techs are doing with this Excel report. And we would literally sit down with them side by side and see what they think about these Excel reports. And sometimes we even went to Jupyter notebooks available on the web that they can access to look at it. Some things we find over and over again is that, particularly in organizations that are new to ML, nobody trusts the model. And that's okay. Even I don't trust the model at first. So what do we do about that? We do a number of things. We use some explainable AI models. There's algorithms. There's actually a really great paper called the Shapley metric. That's, I think, the way to do explanations of any sort of classification regression algorithm. So we use that to do to show why the algorithm is making predictions. We do a lot of sensitivity analysis. They ask what if questions. Hey, look, does the averages match up with what I'm expected for this coming out of the model? Hey, I've seen this particular thing happen. The PSA goes above this, and the failure should go up. Does your model predict that? We do a lot of sensitivity analysis of that nature to really gain trust in the model. And this is actually really good because this feedback loop oftentimes helps us find errors in the model, errors in the data, potential bugs and stuff like that. But in the end, the message is, this isn't magic. This is the heuristics you know in your head codified as a mathematical model. And so it's a very important part of making a machine learning system is making the end user have trust in it, and there's ways to do it. The second thing is that just delivering the predictions is never enough, and I'll go into examples in a second. In the end, people are trying to make decisions. They want a workflow tool. They want a workflow app. And so we are always making user interfaces to the predictions. And oftentimes there's a very collaborative process with the engineering teams of our clients. But the key takeaway for me is that like just AI on its own is never enough. You have to build the UI for the AI. You have to parse how people are using it and make that middle layer so the human can interface to the predictions. So let me make that real. So I know this is a lot of words. For our baby registry example, one of the key problems that they wanted to solve is they're going to make product changes. I want to make a product change, a very specific one. I'm going to force people to take certain key actions. Like there's 10 things I'm going to force them to do on the first day that they sign up. If they do it, they get a free box of goodies. They literally will get a $10 box of samples in the mail. They're going to run this promotion for a few weeks, and they want to use our model to figure out, was this a good thing to do? My cost of customer acquisition now is much higher, but is it worth it in terms of the potentially higher LTV I'm getting out on the other side? Turns out that just delivering predictions isn't enough. They're like, what am I supposed to do with this? How do I make sense of this? What they really wanted when you get down and work with the marketing and the product people, they wanted to run a temporal A/B test with the predicted LTV. And so what we ended up building for them is a small web app that actually you can put in two registries, like a CSV of registries in cohort A, CSV of registries in cohort B. It makes the predictions, and it even does, and there was actually some cool math involved here, where we had to do a modification of the t-test, where there's an additional error term. There's not just sampling error, but there's also a prediction error, because I'm doing t-tests on predictions. And you can use that to then say, okay, these LTVs for these two cohorts that could be of different sizes is materially different, and is statistically significant. So we ended up making a workflow tool to solve the actual business problem that they cared about. In the oil and gas example, what we found is what the algorithm was doing is predicting high probability of failure for a lot of units over and over and over again. And we're like, cool, this is doing great. Look, these things are going to fail in the next few days. The maintenance techs looked at it, I was like, oh, that's actually in the DJ Basin, Colorado. We're running those machines way out of spec. They're running them way harder. They fail all the time. That's not news to me. We're running it in a regime where they will fail often. It's just known. Like with this customer, there's high line pressure in the basins there. There's this is not telling me anything useful. We're like, oh, okay. They're like, tell me something useful. What's useful? And so we worked with them and figured out that, okay, what they really care about is if normal units are starting to look bad. And so in the end, what we did is we actually have another model running on top of the prediction time series. The predictions are coming out once every 4 hours. We run a time series model on that's looking for significant changes in those predicted probabilities, and we alarm on that. We make that available in the UI as kind of the units that should be triaged. Once we did that, what we found out is like the techs were spending, oftentimes 20 to 40 minutes trying to triage what is happening. Why is the probability changing? what we ended up doing there is we ended up actually taking the tree shape algorithm. So this is made by Scott Lundberg out of University of Washington. It is the solution to feature importance in tree-based algorithms. Because it makes a prediction, for every prediction, it tells you why it made the prediction. And like what features drove that prediction. We ended up showing the plot, the tree-shaped plot underneath each of the predicted probabilities, and that helped them triage much faster. That 20 to 40 minutes went down to 5 minutes because they knew exactly which sensor time series to go look at, and when they go log into the PLC at the edge, they knew exactly what registers to go look at. It helped them, their triage process, get much, much better. So again, the feedback allowed us to make this UI that made delivering business value much, much, we were able to deliver much better business value much more quickly. So that's it about my talk. I didn't get a chance to talk about some of these other things. I just have some random little cartoon things there. But we actually use Docker from day one. Even when we're doing modeling, we are doing it in Docker containers because it just allows you to scale and deploy so much easier. When you're engineering, you want to be the Navy. You want to be regimented about how you're doing it. Machine learning, data science is fundamentally software engineering. Use good software engineering practices. And then there's all sorts of other tricks and tips in the modeling world that we have. But we're writing some articles about this and this process, and we're continuing to refine it. But I think that's it for me today. If you guys have any questions, I'm happy to take them. I have about 10 minutes left still. Yeah, go ahead in the front. Yes. Totally. Yeah, and this is, I'm not going to pretend like we came up with this in the vacuum. This is inspired by DM Crisp. This is inspired. Oh, sorry. They asked the question was, are you familiar with DM Crisp, which is a data mining framework for getting value out of data mining quickly? And so, yeah, we are inspired by DM Crisp, human-centered design, lean startup, agile software. All of these kind of came together. We're fleshing out some of these things even more for the world of deployed machine learning solutions. I think Crisp DM was kind of in a world of it was more about just describing what is happening in a data set, not deploying machine learning solutions as products. In the blue.
A couple of questions. Number one, you didn't talk about overfitting. What was the experience with dealing with overfitting? Second, are your models autodidactic in nature, which means are they learning by themselves? Did you employ any champion challenger sort of methodology, model management sort of techniques to manage your models? What are your thoughts on those two things?
Yeah, so the first one was overfitting. Yeah, so overfitting is always an issue in machine learning. And I think we're doing cross-validated learning, particularly for the tree-based models. We're doing cross-validation, and then we're looking at the cross-validated error and seeing, if that's starting to go back up, we're overfitting. Don't fit beyond there. That's why I like to start with random forests, for example, because they're very robust to overfitting. For gradient boosting and deep learning, you have to be much more careful about that. There's ways to do that. On the other side, the models, so V1, typically what we deploy, for both of these examples, for V1, it was manually made models. So we made for the baby registry example, right now what is deployed is the random forest-based model. We made it offline, we put it in the S3 bucket, and then the prediction engine, the inference engine just picks it up from there. And if you want to go change it, once a month, whenever they want to, they will go retrain a model on new data, like additional data, and do it. V2, which we actually are working with them right now, is we're making that continuously retraining. So it's retraining every night. But it's the same model. We're not doing a hardcore hyperparameter search there. Now, I know that there's tools and techniques to do that, data robot, teacup in Python to do that. But that's kind of how we approach that problem. Again, V1, get something into production that is just manually deployed, and then V2, start that continuous retraining with a sliding window, typically. 5 years in the past is not as relevant as the last 2 years, and so we're sliding windows like that. Any other questions? Cool, guys. Thank you.